Good morning, sir.
Good morning, all of you. So, without wasting any time, let us start with the discussion, right? Last class, we were discussing about isomerism, yes or no? So, what type of isomerism we have discussed? We have been discussing about structural isomerism and stereoisomerism. In the structural, we have seen linkage, hydrate, ionization, coordination isomerism, and different ways to figure them out. And in the stereoisomerism, we have been discussing about geometrical and optical isomerism. So, for what type of complexes we have seen? Coordination number 2, coordination number 3, coordination number 4. For 2 and 3, there is no optical activity because plane of symmetry is there. There is no geometrical isomerism because if you switch the groups also, obviously there is no different compound obtained. For the coordination number 4, you can have two possibilities, sp3 and sp2. sp3 means tetrahedral. In the tetrahedral scenario, there is no geometrical isomerism, but there can be optical activity whenever you have all four different ligands. In the DSP2, that is square planar complexes, there is no optical isomerism, but there can be geometrical isomerism that depends upon the complexes given to you. So in that context, we are looking, students. And the last point, the last example which you have seen is geometrical isomers of the compound MABCD of coordination number 4, of course, MABCD. And if you look there, you are getting 3 geometrical isomers and 0 optical isomers. Got the students? This was a summary of the previous session.
Yes, sir.
Yes. Okay, fine. So now if you look at the 3 compounds, whatever I have been discussed, like M, A, B, C, D. So all 4 ligands are different. So 3 geometrical isomers are present, but no optical isomers due to presence of plane of symmetry. So these are the ligands M, A, B, C, D. So these are the different compounds, whatever I have been given to you. So M, A and B at 90 degree, D and C like this. Switching the positions of D and C ligands, you are getting MAB, C and D. So these two are different compounds. Same M compound present here, and switching now AB positions, like you are making AB at an angle of 180 degree. So in that case, you are getting AB at a 180 degree angle, CD again opposite. This is going to be your third compound, right? And these are their animations. So 3 geometrical isomers. And next, in the coordination number 4 only, we can have complexes like MAA taken twice or MEN taken twice. Find it out. MAA taken twice. Yesterday I have told you what do you mean by A, capital A?
Bidentate
Bidentate ligand.
Yeah, bidentate symmetrical ligands. So MAA taken twice. So what is going to be your MAA taken twice now? So you can have an example like MEN taken twice, ethylene diamine. Now MAA taken twice, optical activity and geometrical isomerism. It will be showing or it will not be showing.
It will not be showing.
No, sure.
Yes. Let us look at the animation now. So MAA taken twice, example MEN taken twice, ethylene diamine. Ethylene diamine is a symmetrical bidentate ligand. Like this one, you are having the compound CH2NH2, CH2NH2. The lone pair of electrons on nitrogen, they are donating the
CH2NH2, the lone pair of electrons on nitrogen, they are donating the.
Yes, Dolly, any doubts?
Yes, Dolly, any doubts?
Okay, fine. CH2, NH2, CH2, NH2, lone pair of electrons on nitrogen, they were donating their electron pair to the metal. Same happens from the other ethylene diamine. So we have 4 coordinate bonds. Now you try to switch. Now you try to switch this nitrogen to the other nitrogen position, or this nitrogen to the other nitrogen position. If you try to switch also, you are getting the same compound. You are getting the same compound. And some of you might argue, sir, like in case if you have isotopes, like here if I have N14 and the other we have N15, so then we will be having a difference or not? Yes, that would be mentioned as a difference, yes or no? But you don't consider. Mostly the isotopic effect in the formation of complexes was very, very rare. So that's why that has been not taken into account. Okay, because if you try to switch the compound like nitrogen to N15, that may be easy by doing it theoretically, but practically having such compounds are not so easy. In case if you have isotope, like one of the nitrogen is N15, all remaining are N14. Like 2 nitrogens are N15 and 2 nitrogens are N14. Then you have the possibility or not? Like 2 same nitrogens of N15, they are on the same side, that will be referring to cis. And 2 same nitrogens of N15, they are on the opposite side, that will be representing to trans. But as I have told you, such complexes are not possible. So you can say no geometrical isomerism and no optical isomerism. So whenever we have MAI taken twice, so same symmetrical bidentate ligand, no optical activity, no geometrical isomerism. Now you take unsymmetrical bidentate ligand. Do we have optical activity? Unsymmetrical bidentate ligand?
No, sir.
No. Yes or no? Even this is symmetrical or unsymmetrical, optical activity will not be there because of the presence of square planar plane of symmetry. But do we have geometrical isomers?
Yes, sir.
Yes, geometrical would be there, like M AB taken twice. So like glycine hetero. So A is a different atom, B is a different atom. A is a different atom and B is a different atom. They are two different donor atoms present in the same bidentate ligand. So B is also donating electron pair. A is also donating electron pair. So when two A types are on the same side, then that will be referring to cis. If they are on the opposite side, that will be referring to trans. And you again have a plane, right? So there will be always a paper. There will always be a paper which is passing through that. There will always be a paper. So in that case, what you can say, students? In that case, obviously, you are not going to have, in that case, obviously, you are not going to have optical activity, but geometrical isomers are present. Right? Is everything clear so far?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, very good. So try with the next type of complexes. Try with the next type of complexes. Like next we'll be having a different other complexes. Like coordination number 6. Until now we have discussed coordination number. Until now we have discussed coordination number 4, coordination number 3, and coordination number 2. Now we will be discussing coordination number 6. But the rules are same. Whether it is a coordination number 2 or coordination number 3 or coordination number 4, what are the rules? We stick only to one thing. If you have a plane of symmetry or center of symmetry, it is optically inactive. If we do not have a plane of symmetry, optically active. Yes or no? If we change the positions of the groups and we are getting a different compound, then geometrical isomers are possible. If not, not possible. So now isomerism in octahedral complexes. So coordination number 6, and we have to look at the complexes. We have to look at the complexes of different types. First complex Ma6. All the 6 ligands are same. So all the 6 ligands are same means you can have a scenario like this. Yes or no? Like it is octahedral. Octahedral means what? Imagine this paper. So at the center you have metal. 4 ligands, like 4 same ligands A at 4 corners of this square. One ligand above, one ligand below. All the ligands are same. All the ligands are same. Switch any ligand. So not going to be changing. Yes or no? Whatever the ligand you want to switch, you switch the position. What you are going to happen? You are going to again result in the same compound. So no geometrical isomers. Now look at any plane. Like I can consider a plane like this. I can consider a plane like this. Look, this is very important. In this complex, it is simple, MA6. In the upcoming complex also, you have to look at very different kinds of planes. What are those planes? So I can look at plane like this. Yes or no? Here I have a paper, one bond above, one bond below. I can consider a plane, another paper, which was passing to the top bond. Yes or no? Like this. The plane can be passing through like this or not. Similarly, in the bottom, that is one plane. I can also have a plane, diagonal plane, which is passing through this atom and this atom diagonally. Yes or no? Like this plane. Other diagonal also I can have. So like this plane. Are you understanding, students? I can also have a plane which is exactly like this, not passing through the atoms, but like this. I can also have a plane like this. So different types of planes I can choose. Different types of planes I can be choosing. I can, if we have a square plane like this, one bond above, one bond below, I can choose a plane like this exactly. I can choose a plane like this, diagonal plane, passing through the two diagonal atoms, this plane. So you consider most of the planes here are plane of symmetry. We require at least one plane, that's it. If there is at least one plane which is symmetrical, obviously that compound is optically inactive. Here there is no question of optical activity because this was a scenario. And the ligands are not actually touching each other. They do not have any overlapping. Just we are introducing that. Just we are connecting them with the dotted lines. Why? Because to understand how the geometry looks like. You consider a plane passing through like this. With respect to this plane of symmetry is there or not? Obviously it is there. So obviously this plane is a plane of symmetry. I have just considered one plane. You can choose other planes also. So plane of symmetry is present, so optically inactive. So now in the same way, you try to figure out next complex is MA5, MA5B. So I have just changed one of the ligand. Does it have geometrical isomers and optical isomers?
No, sir.
MA5B. So just one position I have changed, one ligand I have changed. So one ligand I have changed. Faizan, can I keep that ligand on the, like I have a plane like this, right? Can I keep that B above and can I keep that B on the square plane and can I say they are different or same?
Same.
Same. So that means you don't have any ideology with this above and this one. Any difference?
No, sir. There is no difference.
No
As
difference
it
actually.
is.
Yes, very good. Because you need to understand one more thing, students. Whatever the square plane you are considering like this, square, you are saying this is square, right? You leave these two diagonal atoms, and connect the remaining four, like these two diagonals, one above, one below. You connect them four, again you are getting a square. Yes or no? If you remove these two diagonal atoms and consider remaining four atoms and connect them, again you are getting a square plane. With respect to this square plane, this atom is above and the other atom is below. That means not only this is one square and not one atom above, one atom below. We can also have a square like this. We can also have a square in the diagonal manner like this. This atom above, this atom below. We can also consider a square like this. Yes or no? So this atom will be above, this atom will be below. So that is how you need to understand the symmetry of octahedron. That is how you need to understand the symmetry of octahedron. Right, students? So in the complex MA5B also, wherever you keep the next B type of ligand, so plane of symmetry obviously is present. So optically inactive and no geometrical isomers, no optical isomers. Is that clear, students?
Yes, sir.
Yes, sir.
Yes. Yes, very good. Next, consider the complex MA4B2. MA4B2. Do we have geometrical isomers? Do we have optical isomers? Do we have or not? MA4B2. Next complex.
2 geometrical isomers.
MA4B2, write down. No optical isomers, but 2 geometrical isomers. Where do we have geometrical isomers? Geometrical isomers means cis and trans. So I can have a scenario like this. Cis means what? Cis means,
On the same side.
yeah, the two groups should be at an angle of 90 degree as far as coordination components are considered. So I can have MA4B2, right? So I can have 1B here, 1B here. Like I have a square plane, 1B was above, other B was on the square plane. So angle is 90 only. So 90 degree angle. So they are same side only. So remaining all can be A. Can I say different other compound like this, students? And 1B above, other B below. So this is your cis, you are saying, okay, fine. This will be your trans, no issue, because the two B are opposite, so 180 degree. So can I give a compound to you like this? M A B B, and call it as a differences when compared.
No, sir, it's same.
Same, sir.
Sir, this is also in the cis form.
Is my audio and video clear?
Yes.
Yes, sir. Yes, sir.
Yes, right. Yes, right. So now we are looking at the complexes. I have written a complex like this. M, like this is your square plane now. This is your square plane. And this B was above, this A was below. Now this is your square plane. This A was above, A was below. So is the first and third component different or same?
Sir,
Same.
So they are same. Okay, that point you need to understand. So you should not count it as a different compound. Why? As I have told you, there is not a square plane only on this 4. There can also be a square plane like this. 1, 2, 3, 4. There can also be a square plane like this. 1, 2, 3, 4. Okay, so these are same only. Okay, these are same, not different. So you should not count this as third one. So if you want to look at the plane of symmetry, is the plane of symmetry available in trans? Obviously, I can consider a plane like this or not? I can consider a plane like this. This is nothing but your plane of symmetry. So plane of symmetry present. So transform is optically inactive. So what about this form? Plane of symmetry present or not?
no, sir.
No.
Present, sir.
Sir, present.
So where it is present? I'll consider
The
plane now.
diagonal planar.
Yeah, I'll consider diagonal plane now. Like I'll consider a plane where this B is already included and the top B, bottom A. Like this is my plane now. Yes or no? So in the first compound, what do we have? We have A here, A here, A here, B atom somewhere here, B above, A down, right? I'll consider a plane like this. Which plane? So this plane. The plane which I have considered the diagonal plane, that is already passing through the B atom, this A atom, the top atom and the bottom atom. So with respect to the diagonal plane, only one side we have A, the other side we also have A. So plane of symmetry is present. Okay. So plane of symmetry present means optically
Inactive.
right. Yeah. So these animations are useful to understand in the class, but in reality, when you are trying to solve problems, you should have your own visualization. Okay. So whenever I show you the animation, then keep a plane of symmetry, and then if you are understanding, that is not a good sign actually. Okay. These are good. The animations are very good to understand, to visualize, but you should have your own visualization without these pictures in the brain itself. Okay, then only we could solve all these problems. So this is your plane of symmetry in the CIS. You can consider a plane like this passing through all these four. Here, this plane which is passing through. So Ma4B2, no optical isomers, but two geometrical isomers, right? Very good. So that is how you can actually have a plane of symmetry. If you look at the animation clearly, so here you will be having a plane which is passing through this B atom, this A, bottom A. You have a plane of symmetry. Similarly, in the trans also, you will be having a plane of symmetry. Next part, next type of complex, Ma3B3. Ma3B3. Ma3B3, these complexes were given special names. Write down this important. There are no optical isomers. Why? Because again there was a plane of symmetry, but where is the plane of symmetry? We have to figure out. Two geometrical isomers are there. Instead of cis and trans, they were given names facial or FAC, meridional or MER. Plane of symmetry is present, so both are optically inactive. So what is your facial? What is your meridional? What is facial, students? Anyone?
On one side of a triangle, three atoms making a triangle.
Yeah, facial means what? Face. Like if you look at
One
octahedron,
side of tetrahedron.
yes, if you look at octahedron, in the octahedron, if you try to connect this top atom with these all four atoms, you consider this top atom and any set two atoms, any set of two atoms. This our top atom I have considered. Here I have a plane, right? Top atom I have considered. I am considering these two atoms. You connect these three, you are getting one phase. That is one phase of the octahedron. Similarly, this top atom, the other two atoms, you are connecting one more phase. Top atom, one more two atoms, one more phase. Top atom, other two atoms, one more phase. Similarly, from the bottom atom also, we have phases. How many phases are there? 8 phases are there. Yes or no? From the bottom also you can have phase like this. This side also we can have phase like this. This side also we can have phase like this. This side also we can have phase like this. So from the top atom, considering any set of two atoms in the square plane, you can get one phase. That is nothing but a phase of an octahedron. If the three atoms, like the three monodentate ligands, like A3 or B3, if they are forming one phase, then that is said to be your facial or FAC isomer. Yes or no? Look at these three now. So here it is a bottom atom. So bottom atom and these two atoms. If I connect all these three, I am going to get one phase of the octahedron or not? I am going to get one phase of the octahedron. So that is why the name facial or FAC isomer. And meridional means you are not going to get that particular phase. Yes or no? So you cannot connect the three atoms and you cannot generate a phase of an octahedron. And then that scenario or that type of complexes will be leading to your meridional isomer. Look at these students. So facial means you are getting a phase of the octahedron. Yes or no? This is nothing but your phase. Understood this point or not? Whenever the three same type of atoms, if you try to connect, you are getting a phase. Then that is said to be facial or FAC isomer. If you are not getting a phase, then all such kind of isomers are same, which are also called as meridional or MER isomers. So Ma3B3 gives two types of geometrical isomers, FAC and MER. And now look at the optical activity. Is it the facial and the meridional one optically active or optically inactive? Optically inactive, they have already mentioned here. But where is the plane of symmetry? That's what I'm asking. Where is the plane of symmetry? Can I consider this plane? In the facial, if I look at, can I consider this plane? Is it a plane of symmetry?
No, sir.
No, right? Other side we have B, this side we have A. So that is not a plane of symmetry. So what about the next plane? So which is the plane of symmetry there? Can I consider diagonal plane? Can I consider diagonal plane like this? Like this B, this B, this A, a plane passing through these 4 atoms. Other side we
No,
have B, other side we have B, this side we have A. So again, not a plane of symmetry. Can I consider this diagonal plane? Can I consider other diagonal plane? In the other diagonal plane also, we don't have the plane of symmetry. In the other diagonal plane, like what is the other diagonal plane? If I consider this B, this A, this B, and this A, again you are not getting a plane of symmetry because this side you have B and the other side you have A. So diagonal planes are not symmetrical. The plane passing just through top and bottom and dividing it into 2 parts, that is also not symmetrical. Now you have one more plane like this. A plane is passing through top of B and bottom A, but it is dividing in this manner. Is it plane of symmetry? Yes or no?
sir. Yes, sir.
Yes, sir.
Yes or no? This plane was actually like we have metal here, B and B, A and A, B and A. So we have a plane like this. That plane is actually dividing like one B other side, this side B, B A other side, this side A. So this is your plane of symmetry. At least one plane of symmetry we should have. Okay. So whatever the plane you consider, it cannot be a plane of symmetry. If you have at least one plane of symmetry, obviously that will be leading to optical inactive nature. So that is your plane of symmetry. What about meridional? Meridional is simple, right? I can have a plane like this, like considering a plane, like removing out this A and this A, I'll consider remaining all other atoms. So this is one A and this is other A. So with respect to that plane of symmetry is present. Are you understanding, students, where you are choosing the plane of symmetry?
Yes.
Yes, sir.
Yes, right. Very good. So in the Ma3B3 type, we are not having any optical isomerism, but we do have 2 geometrical isomers, which are called as facial and meridional isomers, which are called as.
Sir,
Yes, please.
sir, I cannot understand plane of symmetry for these compound.
Yeah, look at carefully. So what is your facial? Let us consider facial. Okay. So you can just visualize the facial, whatever the same compound given to us. Okay, I'm just erasing this. Concentrate on facial. Now where do we have A? So this is your square plane. Metal is at center. Here we have A, here we have A. Here we have B, here we have B. Yes or no?
Yes, sir.
One B above, other A down. So A. So we are getting on face. So that is why it is said to be facial isomer or FAC isomer. Now I am considering a plane like here I have A, here I have A, here I have B, here I have B. Above A, above B, below A. I am considering a plane like this. Which plane? I am considering a plane like this, diagonal plane. If I consider a diagonal plane, this side I have B. This diagonal plane itself indicates these 2 atoms, these 2 ligands, one top ligand, one bottom ligand. So if it is my plane of symmetry, if it is my plane, then this side of the plane I have B atom, other side I have A atom. So which is not symmetrical, obviously. So that is not your plane of symmetry. Consider other diagonal plane, this plane. If you consider this plane also, this side you have B atom, this side you have A atom, again not symmetrical. Now what I am doing is I am considering this plane, this plane. We have a plane like this or not? Yes or no?
Yes, sir.
Exactly dividing it to half. Here we have A, here we have A, here we have B, here we have B. Top B, bottom A. I am considering a plane like this. This plane is actually passing through top B, bottom A, and it is not passing through any of the atoms on the square plane, but just bisecting the distance between them. Just
Yes,
bisect the distance between them. So if you consider a plane like this, obviously this side what I have, B here, A here. This side what I have, B here, A here. Symmetry or not?
Yes, sir.
So that is your plane of symmetry. That's what I'm just dividing the plane. I'm just dividing the total square plane in such a way such that the back side I'm going to have BA and the front side I'm going to have A and BA. So which was symmetry. And the top atom and bottom atom, they are already included in the plane. So that is your plane of symmetry. Got it now?
Yes, sir. Got it.
Yes, very good. So that was your plane of symmetry. So what is the plane of symmetry? So the plane of symmetry is actually passing or bisecting the distance. So here you have B, here you also have B, here you have A, here also you have A. And this is again passing through the top B and passing through the bottom A. So that is nothing but your plane of symmetry. Here I think you can easily figure out in the meridional. Yes or no? Meridional case. Yeah, we have meridional again, right? We'll write it down. Yeah, in the meridional case, you have the scenario like this. Yes or no? So you can consider a plane. Which plane you will consider? You consider a plane like this. So with respect to this side, back side is A, front side is also A. So again, this is plane of symmetry or not? Yes or no? There is a plane of symmetry here also. So I have just considered a plane which is passing through all the 4 atoms except these trans pair. So that means you can have a shortcut here. Whenever you have 2 atoms which are in the trans fashion, obviously there will be a plane of symmetry. Like you have any set of compound, if the compound is given to you like this, M, A2, B, C, D, E. I have 2A, 1B, 1C, 1D, 1E. So if the 2A, if they are trans, if you are having compound A, 1A and the other A opposite are there, you can pass the plane to remaining all 4 atoms. Since these 2 A and A are opposite, so you will be having a plane of symmetry. Understand this point carefully. Whenever you have a trans pair, like 2 atoms which are exactly opposite to each other, then obviously there will be a plane of symmetry in coordination number 6 compounds. Understood, students? So whenever a pair of same monodentate ligands, write down this point, same monodentate ligands are trans to each other, that is at an angle of 180 degrees to each other, then there will be a plane passing through remaining all 4 atoms. There will be a plane passing through remaining all other atoms. Here the atoms are ligands or other groups, you can say ligands. Okay, then there will be a plane passing through remaining all other ligands or groups, which is symmetrically dividing, which is symmetrical. Okay, that is plane of symmetry is present. Whenever plane of symmetry is present, optically inactive. So this is a scenario in the case of for coordination number 4 and 6 compounds. In the 4 again we are talking about square planar DSP2. Write down this point, students, very important. For coordination number 4, in the 4 DSP2 hybridization like square planar complex and octahedral complex, whenever there is a pair of same monodentate ligands which are trans to each other, that means they are at an angle of 180 degree to each other, then there will be a plane passing through remaining all other atoms. which is going to be symmetrically dividing. That is, plane of symmetry would be present. That means that is optically inactive. Optically inactive. These are very important because whenever you are increasing the type, like if I have a bidentate ligand, if I have M A2 B2 C2 type, then you will be having a lot of possibilities. In that possibilities, how many are optically active, how many are optically inactive, that we have to figure out. That will be time consuming. So we have to go with some logic, some idea, then only we'll be getting it correctly. Anyways, note it down, students. Note it down and let me know if you're done. Nandana, got it or not?
Yes, sir. In meridional, on the when the passing the plane, sir, on all the four sides it's not B, right? One side it's A, so how are we calling it symmetry?
No, which plane you are considering in the meridional?
Sir, A on opposite sides on 80 degree.
So this is what the plane of symmetry I have shown you, right?
Yes,
Yes or no?
sir.
I am passing the plane to this B atom, 1 atom, 2 atom, 3 atom, 4 atom. These are all in the plane only now. So
Yes,
backside,
sir.
okay, you are passing a plane. In the plane itself, we have one B atom top B, one bottom B, one B on the square plane, the other A on the square plane. With respect to the plane, opposite side you have A and the back side you have another A. So this is A. This is your mirror now. Okay. On the back side of mirror, what do you have this A? On the front of a mirror, what do you have this A? Symmetry is there or not?
Yes, sir. Okay, yes, sir.
Okay. So you are getting a doubt like you are considering different plane. Like sir, you have 3 A atoms on the square plane, only one B. So how can be symmetrical? No, not like that. In the plane of symmetry, whatever you are considering, in that plane itself, we have some atoms. Like the top B, bottom B, this B atom and this A atom, they are already in the plane. So with respect to this plane, one A is a back side, the other A is front side. So this is your mirror now. So this is back, this is front. So that is plane of symmetry.
Yes, sir. Got it, sir.
Okay. Is that clear to everyone, students? All of you should
Yes,
respond.
Yes, sir.
Yes, very good. Next, look at the complexes like Ma2, B2, C2. It will show geometrical isomerism and optical isomerism also. So which complexes are going to be showing, or how many geometrical isomers are there? So you have to answer this question now. Ma2, B2, C2, how many stereoisomers are there? You try to answer. So you have to look at the possibilities then. It is not so simple. Yes or no? Ma2, B2, C2, the complex is Ma2, B2, C2. So how to start? Anyone? What, Suman? What is the total number of geometrical isomers and or total number of stereoisomers?
Don't know, sir. I forgot.
Faizan Khan? So write down. So what are the possibilities you are going to get? What are the possibilities?
5 geometrical isomers.
5 geometrical isomers. Okay. So why? How to write the possibilities? You have to better write the possibilities in such a way such that. So M atom is there. You have to split these ligands into sets. So both the A are trans, both the B are trans, both the C are trans. Like what do you mean by this, students? In the bracket, what I have mentioned? M is the central middle atom. This A and this A, they are trans to each other. That means they are at an angle of 180 degree. B and B, again they are at an angle of 180 degree. C and C, again they are at an angle of 180 degree. Yes or no? That is your first compound. Now I can have same M metal. One set is going to be trans, A. Remaining two are not trans, like BC, BC I'll have. Now what I can say, this one B and other C, they are at an angle of 180. this B and this C, they are at an angle of 180. That means 2B are not at an angle of 180. B and C are at an angle of 180. Next, M. I can have AA earlier trans, right? I can have BB trans and AC AC. M. I can have CC trans. I can have, like in the first case, what I have? AA trans, BB trans, CC trans. Second case, AA trans, BC, BC are now trans. That means BB, CC are not trans. Second case, third case, BB is trans. Fourth case, CC is trans. So you have AB, AB. This is how you can write the possibilities. Last case, we can have nothing is going to be trans. So AB, BC, CB. So these are the different types of compounds. Okay. If you look at the first compound, how you can understand the first compound? First compound was like this, M. A and A are trans. What do you mean by that? That means if one A is here, the other B should be exactly opposite, 180 degree. B and B again trans. So if one B is here, other B should be exactly opposite. C and C again trans. So one C above means other C should be exactly opposite. You may ask a question, sir, why you are keeping A and B on the square plane? Why not on the why not A or A you are keeping here? You can do that, not an issue. You can place A here, M, A. You can place C here. You can place B here. Both the compounds same or different? These two compounds. These two compounds are same or different? What are the compounds?
Same.
Same, right? So they are same. Okay. So only condition is A and A is at 180, B and B 180, C and C 180. So that's how we have drawn compound 1. How to draw compound 2? M, A and A are at an angle of 180. So 1A if you keep above, the other A you can keep below here. B and C at 180. So that means B is here means C should be at an angle of 180. Again B and C 180. So B here means C should be at an angle of 180. So you can change the positions. Like if you want to keep C here and B here, then also same or not? If I keep B here, then both B are 90 degrees. If I keep B here, then both B are again 90 degrees. B and C are at an angle of 180 degree. The condition is B and C are at an angle of 180 degree. That is how you can draw the second type of compound. Third type of compound, how you can draw? Is first, second, third, fourth, and fifth. Third type, how you can draw? Third type is similar to second type. Only difference is you have BB trans. What about AC? A will be here, C will be here. Again AC, because A and C are 180 now. A and C are 180 now. If A and C are 180, automatically A and A are at 90. A and A are at 90. Fourth type, M, C and C are 180 now. C and C 180. AB 180. Again AB 180. So if AB are 180, automatically AA and BB are 90. Fifth type AB 180. So A here I have, B should be here. BC 180, CB 180. So these are the 5 compounds which you can draw, students, which you can draw 5 different possibilities. Now if you look at compound 1, 2, 3, 4, at least a single trans pair is there or not? At least one trans pair. In the compound 1, everything is trans, AA, BB, like same type of ligands are trans. In the second compound, same type of ligands, AA is one trans is there. In the third compound, same type of ligands, BB, one trans is there. In the fourth compound, same type of ligands, CC, one trans is there. So at least one trans is there. What I have told you previously. If there is at least,
Chain of symmetry is present.
very good. If there is at least one trans of same type of ligands, then obviously there will be a plane passing through remaining all 4 other atoms, which is going to be symmetrically dividing. So compound 1, 2, 3, 4, they have at least one pair with the same ligands in trans. Same ligands in trans. In the compound A, all are same, all are trans. Compound B, AA, same type of ligands, trans. Compound B, compound 3, compound 4, again you have trans, same type of ligand, trans. So 1, 2, 3, 4. Are they optically active or optically inactive? So
Optically inactive.
Inactive.
optically inactive. What about fifth compound? You fifth compound you take and you try to look at different planes. Whatever the plane you want to consider, you consider. I'm considering a diagonal plane first. You consider a plane like this. You include atoms, all the 4 atoms, A, C, B, B. If I include these 4 atoms, obviously other side is B, this side is C. Again, not a plane of symmetry. If I include this B and this A, this B and this C, this side is B, other side is C. Again, not a plane of symmetry. If I pass a plane like this, BB is symmetrical, but CC, is that symmetrical or not? CC again symmetrical, right?
Excuse me, sir.
Sir,
Yeah,
here in the last one, why CB is taken? Why not CA?
yeah, CA you
Sir,
have
in
to
the
take.
fifth,
Yeah,
yes, sir.
that was a mistake actually. That's why I'm thinking from where we are getting 3. It is MA to B2, right? But we are getting 3B. Yeah, that's true. This is CA, AB, BC, CA. This is A. True. That is just mistakenly written. So if you consider in this plane also, again A and B, C and C, not symmetrical. You consider any plane, students. You consider whatever the plane you consider, like M, A2, B2, C2. Since there is no set of same ligands which are trans to each other, so obviously, is there a plane of symmetry here?
No, sir.
No plane
No,
of
sir.
symmetry. No plane of symmetry means what? No plane of symmetry means you will have 2 optical isomers.
Optically active.
2 optical isomers means 1 enantiomeric pair. 1 enantiomeric pair. Yes or no? So how many number of stereoisomers now? Like in
6.
total you have
Six.
yeah 6 stereoisomers. In that 6 stereoisomers, which are optically active, like how many geometrical isomers are there?
5 and last
How many?
we'll have the 2 isomer.
Yeah, if I ask a question like how many geometrical isomers are there? How many?
Geometrical isomer 5.
5.
5. How many optical?
1.
2.
You cannot have one optical isomer. You'll also have a pair. Okay, 2. How many total?
6.
6. You should not add 5 and 2 because in the geometrical, whatever the one compound you have considered, that compound itself is existing as 2 pairs, like 2 compounds. Yes or no? So 5 geometrical. Yeah, this was the ultimate information. Ma2, B2, C2 shows optical isomers and geometrical isomerism. Trans, all the trans are optically inactive, like AA, BB, CC, AA, BC, BC. And you will have a cis compound which is optically active. So 4 trans, 1 is cis. Yes or no? First 4 are trans, last one is cis. So in total 5 geometrical isomers. Since cis one is optically active, that will be corresponding to 2 optical isomers. So in total you have 6 stereoisomers. Write down the students, all of you. Very important. Ma2, B2, C2 type of complex, you have what do you have? You have 6 stereoisomers, 4 trans plus 1 cis, so 5 geometrical isomers and 2 optical isomers. Note it down, all of you. If you are done, please let me know.
Yes, sir. Done.
Yes, sir.
So look at the animations now, you will get a clarity. So first type of complex M, AA, BB, CC. So there you have plane of symmetries. Second type of compound also AA is a trans, again plane of symmetry. Third type of complex BB trans, so plane of symmetry. So whatever the same are there, they are taken above and below so that you can simply consider square plane as plane of symmetry. Fifth complex AB, BC, CAC. So again you have no plane of symmetry. So obviously fifth compound is having cis and trans. These are very logical, students. You have to work out on these. Okay, it's not directly given answers. Try to answer this now. MA3 BCD. With the same logics, whatever I have told you, take a minute of time. Try to answer this question. MA3 BCD. So how to write the possibilities? You don't worry with this part. I'll give the table to you at last. How many you can mug up with that table? But you have to know the analysis. How we are doing the idea, how we are getting it.
So 4 geometrical isomers.
So 4 geometrical isomers. Okay. How many optical?
No optical isomers.
No optical isomers. Okay. Any other options? Faizan says no. 4 geometrical. I think that is visible to, right? Show optical
सब
isomerism.
चीज समझ में आ रही है
हाँ,
तुम
हाँ,
लिख कितना लिख रहा
लिख रहा हूँ ना वो, लिख भी रहा हूँ साथ साथ।
याद हो जाएगी
Yes, students. MA3 BCD. MA3 BCD. We can have possibilities. What type of possibilities I can have? First, comment on the possibilities. I can have AA as a trans in all the compounds or not? AA trans, AB, CD. I can have a compound like this. AA trans. Now A can be linked with AC, and you can have BD. And I can have AA trans. Like AB I have considered earlier. I have 3 A type of atoms, right? I have 3 A type of ligands. Out of these 3, 2 A are there in the trans position. The third A and B can be again trans. CD again trans. AA, AC, BD. AA, AD, BC. So in all these conditions, the AA is trans, and remaining I have considered A with B, A with C, A with D. Now I can have the fourth case where both A are not trans. Like I can have one A with B, one A with C, other A with D. These are the 4 possibilities or not? These are the 4 possibilities I have. Out of these 4 possibilities, first 3 possibilities have at least one pair of trans where we have the trans scenario with respect to same. Like MAA, MAA, MAA. So AA is going to be trans. Yes or no? So in the first, second, third complexes, what do we have, students? We have one pair of same ligands which are trans to each other. So these are trans. What about the fourth? Fourth one is cis. Because nothing is, no, there are no same type of ligands which are trans. So the fourth one is going to be cis. So how many geometrical isomers? 3 trans plus 1 cis. So in total you have 4 geometrical isomers. So for the first, second and third, first, second, third, fourth. For the first, second and third, since we have same pair which is going to be trans to each other, like same type of ligands trans to each other, in the 1, 2, 3, we will be having a plane of symmetry or not? In the compounds 1, 2, 3, like MA3 BCD type complex is given. If you try to figure out first way, how you can say the complex? M, AA, A above, A below, AB, A and B, CD, C and D. So you can have a plane like this. With respect to that plane, the top A and the bottom A, they are obviously symmetrical. So if you consider any one pair, which is obviously at a transposition to each other. So if you can pass a plane passing through remaining all 4 other atoms, which is going to be a plane of symmetry. So in this condition of MA3 BCD, in the first 3 cases which are trans, you have plane of symmetry. Plane of symmetry is present. Whereas in the cis, plane of symmetry present or absent? You consider cis form AB, AC, AD, you will not get any plane of symmetry. Like A and B are opposite, A and C again opposite, A and D again opposite. You consider any plane, students, in the cis compound, there will not be any plane of symmetry. So obviously cis compound is optically inactive. So cis compound is optically inactive means it will have two optical isomers. So in total, how many stereoisomers? How many stereoisomers in total? 6 or 5? You can have four geometrical, 2 optical. 4 plus 2, you will say 6 optical isomers, or you should say 3 trans or geometrical isomers which are optically inactive. 1 cis is optically active, so 3 plus 2, that will be 5. 5 stereoisomers. Write down this, all of you. You should not say 4 geometrical and 2 optical. Why? Because in the 4 geometrical you have already included 1 cis. That means you are counting one same compound 2 times, which is wrong. So 5 stereoisomers are there. If they specifically ask about geometrical isomers, 4 geometrical isomers. Specifically asked about optical isomers, 2 optical isomers. All of you note it down. Ma3BCD type of complex. Ma3BCD type of complex. You have 5 stereoisomers. Yes. Is that clear, students? Why they he Faizan says 5, 6, 5. Very good. So 6 you should not take, you should take 5. I will give one table to you. You have to memorize the table. You should know the idea also, but you have to remember the table. How many isomers are there? Like for different set of compounds, how many geometrical are there, how many optical are there? So the table you better write down. Is it noted, students? Yes. Yes, very good. So all of you must write down the table then. In this way, you have to do the analysis. Okay, this is how you have to do the analysis. Just a second. Just a second, students. Yes, write down the table here. Complex type. Complex type. GI stands for geometrical isomers. Pair of enantiomers. Number of stereoisomers. Ma6 0 0 0. Ma5B 0 0 0. Ma4B2 2 0 2. Ma4BC 2 0 2. Ma3B3. How many? Ma3B3 means facial and meridional 2. No optical activity 0. And total is 2. Ma3B2C. In Ma3B2C, you have 3 geometrical isomers because one position has been changed. 0 and 3. MA3BCD. Just now we have discussed 4 geometrical isomers, 1 pair of enantiomers, 5 stereoisomers. Note down this. MA2B2C2. MA2B2C2 5 1 6. I'll just complete it throughout. Okay. I'll just complete at all the sets. Then you can do MA2 BC DE. Yes or no? MA2 BC DE 9. 9 is geometrical isomers. 6 pair of enantiomers. Pair of enantiomers. And the stereoisomers is 15. M, A, B, C, D, E, F. 15 geometrical isomers, 15 enantiomers, 15 plus 15, 30 will be the stereoisomers. Write down these, students, all of you. Okay, I'll just go to the previous slide. You can note it down. Okay, this is all the pair of enantiomers, geometrical isomers, and total number of stereoisomers. In the case of monodentate ligands, we do have bidentate ligands. We have to look at those examples as well. Once you are done with the noting part, let me know. I'll be proceeding further. So you know the idea, right? How to look at the isomers. So how to visualize, how to keep look at different possibilities. So like the same way. So for MA2B2C2 we have seen, MA3BCD we have seen. Like that MA6, MA5B, MA4B2, MA3B3 we have seen all this. In the same way, if you try to write down for M, A, B, C, D, E, F, then you will be getting 15 geometrical isomers, 15 pair of enantiomers, and total will be 30 stereoisomers, which is not required to write down all those M, but they have been written and the number has been counted. You can remember it. If they have asked, you have to directly answer it. Okay. So this was a shortcut, and you can just apply it with these numbers. Kanishka, done?
Done, sir.
Done, very good. So then we'll have a complex like MAB4. A means symmetrical bidentate ligand, B4 all are same type of monodentate ligands. MAB4, no geometrical, no isomer, no optical and no geometrical. Why? Why? Because plane of symmetry is there. Okay. Where is the plane of symmetry? That is again a point. You consider a plane like this. You consider a plane like we have two B4, right? 4 B atoms are there. So one B above, other B down. So with respect to this square plane, you are having plane of symmetry. This is symmetrical plane of symmetry present. So no optical isomers. And obviously you change the position of any B or any A. Like you change the positions of A like this. You keep A here, 1A, other A top. This is your bidentate now. This is your B, this is B, this is B, and this is B. This is also same with the same compound given. So no MAAB4 means even though if you are changing the positions of ligands, you are not getting a different compound. And the compound has plane of symmetry, so no optical activity. So no geometrical isomers, no optical isomers. Is that clear, students?
Yes, sir.
Yes, Vaidehi, very good. Then MAA, A2B2. Look at this complex. MAA, AA means symmetrical Symmetrical bidentate ligand. Symmetrical bidentate ligand. Now look at the geometrical isomers and optical isomers. It will show both geometrical and optical. So look at the compounds, how we can write down. So I have a metal here. So first complex is written in this manner. Metal is present here. AA bidentate. You can look at yes or no. Capital A stands for bidentate, A2B2. So this is your bidentate, A2B2. Both the A, like monodentate, can be at an angle of 90 degree. And both the B, one B above, other B below. So they can be at an angle of 180 degree. Yes or no? So this is how you can actually have one compound. And the other compound, what do you have? If I change the positions of A with B, can I change the positions of A with B or not? This is a different compound. And I can have B here, A here, A here. That is different compound. Because now in the first case, whatever the molecule given to you, both A are at 90 degrees, both B are at 180 degree. In the second possibility, like BB 90 degree, AA 180 degree. I can also have the third case. AB, yes or no? AB and AB. Like this can also have. So different ways are there. This is the first possibility, write down. This is the first possibility. MAA, A2B2. In that we are having both the A's 90 degree, both the B's 180 degree. Both the B's 90 degree, both the A's 180 degree. So one first case is A comma A angle is 90 degree and B comma B angle is 180 degree. Second possibility, this one, B comma B angle is 90 degrees, A comma A angle is 180 degrees. Third possibility, look at third possibility. In the third possibility, what do we have? This one, AA at an angle of how much? 90. BB at an angle of how much? 90. Third possibility is AA at an angle of 90, BB also at an angle of 90. So these three are different or not? All these
Yes,
three are
sir.
different. All these three are different orientations or same orientation, matching with anyone?
Different.
Different.
sir.
Yeah, different, right? So they are considered as three geometrical isomers. And which one is optically active?
The last one.
Yes or no? Because we have a pair here, BB 180. So one is trans, not optically active. Again, the second compound, one is trans, not optically active. In the last one, AA 90, BB 90. So there is no trans. So obviously it is similar to cis. So then optically, there is no plane of symmetry. So optically active. So first and second are optically inactive. Third is optically active. Write down that. First and second are plane of symmetry present. So optically inactive. Third one is plane of symmetry absent. So optically active. Got it now? This isomerism is very like more like visualization. You have to visualize the molecule. Octahedron you have to keep in your mind always. Okay, let us proceed then. So whenever I have a compound like this, like at least one pair trans to each other, then I have the square plane which is plane of symmetrical. In the third way only, I do not have any trans. Yes or no? Is there a trans? No, no possibility is there. So that is why it is optically active. MAA taken thrice. Next complex. We have seen the complex MAA A2B2. Earlier MAA B4. MAA A2B2 shows geometrical isomers and optical isomers. How many geometrical isomers it shows? MAA A2B2. 3 geometrical isomers. How many optical isomers? 2 optical isomers. How many stereoisomers?
Four.
Four stereoisomers. Right. Now look at this. MAA taken thrice, like ethylene diamine taken thrice. So 3 symmetrical bidentate ligands are there. MEN taken thrice. In that case, you will not have any geometrical isomerism, but it will show optical isomerism. Write down this. Optical activity will be showing 2 optical isomers, no geometrical isomers, because no cis and trans, but shows optical isomerism because no plane of symmetry. No plane of symmetry, show optically active. Optically active means how many isomers you have? So you have only one pair, that means 2 optical isomers. One is D isomer, the other is L isomer. Like enantiomeric pair, one enantiomeric pair is there. Okay. MAAB4, no optical isomers and geometrical isomers. MAA2B2, 3 geometrical isomers, 1 or 2 optical isomers. 2 optical isomers. 2 optical isomers means you can write one enantiomeric pair plus 2 optical isomers means 1 enantiomeric pair. Enantiomeric pair. So, or you can combinedly say 5 stereo, 5 or 4. 4 stereo. Next compound MAA taken thrice, 2 optical isomers plus 0 geometrical isomers. Listed down all these, you can remember. Now we are understanding the plane of symmetries, everything else. But when it comes to final exam, you can't waste this much time. Time is a factor, right? So you can remember this set of examples, like some 10 to 15 examples will be there. Remember all number of isomers question asked means you should directly say the answer. Next compound is MAA taken twice also we can have, and a B2. Is it noted, students? Can I proceed further?
Yes, sir.
Yes, sir.
Yes, very good. Next compound is MAA taken twice A2, that is MEN taken twice Cl2. Here write down 2 geometrical isomers and 2 optical isomers is possible for this competition, for this combination. Like metal, like cobalt, you can have a complex like this: COEN taken twice Cl2 whole plus. Cobalt is in +3 state. So whether this particular complex ion is optically active or not? Yes, it is optically active. So what are the combinations we have? So 2 ethylene diamonds are there. So this is one ethylene diamond group, this is other ethylene diamond group. Like whenever they are exactly opposite to each other, like 2 Cl2s or 180 degree and 2 ethylene diamonds again opposite to each other, then in that case trans. Whenever it is trans, optically inactive. Why? Whenever it is trans, I can have a plane like this. Plane of symmetry would be there. So whenever plane of symmetry is there, optically inactive. In the cis fashion, like 2 B atoms are now at 90 degrees, and 2 ethylene diamonds, they are also at an angle of 90 degrees. So in that case, you do not have plane of symmetry. Plane of symmetry is not present. Plane of symmetry not present means optically active. So write down cis form of MEN taken twice Cl2 is optically active due to absence of plane of symmetry. Whereas trans form is optically inactive. So cis form optically active means you have 2 optical isomers like D and L form, like one enantiomeric pair is there, and 2 geometrical isomers. So 2 geometrical isomers, 2 optical isomers, in total 3 stereoisomers. because in the two geometrical isomers you already include cis form. Again in the two optical isomers, again you are considering two forms, means that means counting same compound two times. That is wrong. So two geometrical isomers, two optical isomers, three stereoisomers. Okay, this is the information regarding M, A taken twice, A2 complex. So where you can have complexes like cobalt. Right, students?
Yes, sir.
Yes, sir.
Yes, sir.
That's very good. These are the animations which you can easily understand. Like cis COCl2 En taken twice and a trans COCl2 En taken twice. This is how the complexes look. Like if you look at the animations with the help of indicating all type of bonds, like ethylene diamine, like CH2, CH2, NH2, NH2 we have. So if you indicate all types of bonds, this is how the complexes looks like in reality. And D and L forms of because this form is optically active, right? So optically active means you have D form and L form. So these are nothing but your non-superimposable mirror images. These are nothing but non-superimposable mirror images. Right. So this is all about your isomerism, students. So we have seen coordination number 2, coordination number 3, coordination number 4, coordination number 6. Wherever geometrical is possible, wherever optical is possible, different sets have been studied along with some tables given. So we have to be knowing how to approach and what are the tables given. Let us solve some examples. You will get the clarity now. Yeah, try to solve this. PT NH3 taken twice, NO2 taken twice. So total number of isomers for this complex is how many are possible?
Two geometrical isomers.
How many? Yeah, Faizan, how many? 2. So read the question carefully. What are they saying? Total number of isomers for this complex. That's it, right?
So link isomer also there in this case.
Everything will be there. That's what I'm saying. Total number of isomers means you should not be constraining yourself only to geometrical or optical, right? First, you should know what is the coordination number of this complex. What is the coordination number? Coordination number of this complex.
4.
Coordination number is 4. 4 means, yeah, 4 means you have two possibilities. sp3 or dsp2, like tetrahedral or square planar. Whether it is tetrahedral or square planar, how to know? Look at the metal. What is the metal given? Look at the metal. Metal is platinum.
Platinum, sir.
DSP2.
Yeah, if it is platinum, here the ligands are strong field ligands, that's okay. If it is platinum, every ligand will be acting as a strong field ligand, because there you will not having the 3D. Yes or no? For 4D and 5D, every ligand is strong field ligand. So obviously strong field ligands means pairing of electrons occurs. Pairing of electrons occurs means you will have platinum in the same group of nickel. So you will be having one d orbital empty. So what type of hybridization it is getting? sp3 or dsp2?
DSP2.
DSP2.
dsp2 means inner orbital complex, inner orbital complex. And what is the shape? What is the shape?
Planar.
Square planar. So we have figured out from the geometry, like coordination number 4, what is the geometry of the complex? Square planar is the geometry. So we have what type of system? Metal M is there. One is ammonia NH3. The other is also ammonia NH3. And you have NO2. NO2 means you can have nitrogen linkage, both the nitrogen linkage. NH3. And you can have what? Both ONO linkage. NH3. One NO2 linkage, other is ONO linkage. One NO2 linkage, other is ONO linkage. And it is like Ma2B2 or not? Ma2B2 system, square planar. Ma2B2 system, square planar, it will show geometrical isomerism or not? Yes or no?
Yes, sir.
Yes, sir.
Yeah, Keshav has given the right answer. Very good, Keshav. So it is whatever we are writing here, NH3, NH3, they are at 90-degree angle. So I can make them 180 also. So metal here. So ammonia, ammonia. So NO2, again NO2. So these are different because this is cis, this is trans. Again, both O and O. So metal, ammonia, ammonia, ONO, ONO. So this is cis and trans. This is your cis, this is your trans. Again, this is your cis, this will be your trans. Metal, NH3, NH3. Any other possibility other than the 6? So we have looked at all the possibilities, right? Like both the NO2 are having nitrogen linkage, both the NO2 having oxygen linkage, one NO2 nitrogen linkage, one NO2 oxygen linkage, and we have looked at all the cis transforms. So geometrical isomers were also included. So you have six isomers, and obviously square planar means we don't need to look at the optical activity because all are optically inactive. 6 isomers are possible in total. That is the right answer. Got it now, students? So whenever the complex has been given, you have to look at linkage. Like the question is not about number of geometrical isomers. In that case, you can just go with the cis trans. Is that clear or not?
Yes, sir. Yes, sir.
Yes, very good. Try to look at which of the following compound shows geometrical isomers. Which of the following compound shows geometrical isomers? First one will show. It is like Ma3B. It will not show. Second one, Ma4 will not show. Third one, Ma2B2 will show. Fourth one, Ma4 will not show. Right? Same like platinum, Cl3 means Ma3, C2H4 is B. Metal, NH3 taken 4, Ma4 not show. Metal platinum, A2B2 will not will show. Metal is platinum, Cl4, Ma4 will not show. Next, PTEN taken twice, it will show or it will not show. PTEN taken twice. It is like MAA taken twice.
No, sir. No, sir.
MAA taken twice, square planar, it will not show. So how do you know it is square planar, Ayushi? I'm just asking questions, okay?
4 linkages, sir.
Sorry?
4 linkages.
Yeah, 4 linkage means you can have tetrahedral and square planar, right?
Yes, sir.
Yeah. How do you know?
प्लैटिनम है तो उसके साथ प्लैटिनम इज सो क्या सारे स्ट्रांग हो जाएंगे.
Yes. The scenario. Platinum is a metal which is not having the 3D electrons involving. So obviously all are strong field ligands. Ethylene diamond is strong field ligand. So inner orbital overlapping happens. So square planar is the possible geometry, and it will not be having a tetrahedral. Platinum GLY, glycine 802. It will show or it will not show?
Show geometrical.
So AB type.
Sorry?
Yes, sir, it is AB type. That's what I'm saying.
Yeah, AB type. Yeah, MAB taken twice. That is also showing. Again, last one will also show, right? MA2B2. So it will also show. Simple discussion, students. So we have been discussing the isomerism in detail. So all of you practice this. Why I am going very slow in the isomerism is a lot of confusion arises. Whenever we are looking plane of symmetry, center of symmetry. Center of symmetry is not there as of now. We will be looking at that in the organic compounds. In the Coordination compounds, only thing is plane of symmetry you have to consider. Okay. Fine. This is all about isomerism. Then let us now go with the next part known as organometallic compounds. Can anyone say which is the best organometallic compound which you have been to in the organic
Grignard
chemistry?
agent.
RMGX.
RMGX.
Grignard
Grignard agent acts as a nucleophile or a base?
nucleophile.
Sure. Nucleophile or
Sir,
base?
MGX has a negative charge and
No,
R
I'm
is
talking
a,
about R minus.
it acts as a nucleophile.
R minus MGX,
R
right?
minus first priority to accept the hydrogen. That's why it can be a base also.
Yeah. When it is a base, when it is a nucleophile.
When the acidic hydrogen is there, it's going to
Yes,
act
very
as a
good.
base, and
Very good.
when
Grignard
acidic
agent can
hydrogen
act as a base as well as a nucleophile, but it will act as a base when there's an acidic proton available. Not the hydrogen, acidic proton. That is protons
yes,
connected to,
proton.
yeah. Acidic proton means proton connected to more electronegative atoms, like OH bond. Yes or no? In that case, you can say RMGX can act as a base. It can act as base and a nucleophile. So whether it is acting as a base or whether it is acting as a nucleophile, that is decided by the substrate. Whatever the substrate you have taken, like you have taken alcohol or a phenol or acid, or you have taken a carbonyl. In the carbonyl, you do not have acidic hydrogens. You have you have electrophilic center. So R minus then act as a nucleophile. So R minus, the CH3 minus C2H5 minus has a tendency to act as a strong nucleophile as well as a strong base. But whenever a acidic proton is there, it will be a strong base. If acidic proton is not there, it will be acting as nucleophile. In the organic chemistry, we will be looking at different compounds, different reaction mechanisms, where it is acting as a base, where it is acting as a nucleophile. Why I have said that means the importance of organometallics in the organic chemistry is very high. So what are organometallics? Compounds in which carbon atom of hydrocarbon or a ligand is directly bonded with a metal or metalloid or non-metal. When the carbon is directly bonded with metal or metalloid or non-metal, like non-metal like boron, phosphorus, etc., then that compounds, whatever they are resulting, they are said to be organometallics. You write down the list first. First you write down the list. Identify the organometallic. RMgCl Grignard agent is an organometallic. CH3Ti OC6H5 taken thrice. It is also organometallic. Dialkyl zinc CH3 ZnCH3 organometallic. Al4C3 organometallic or not? It is not organometallic. What type of structure it will have? Al4C3. Al4C3, right? 1, 2, 3, 4. 1, 2, 3. Yes. This is how the structure you are going to have. It is not organometallic. CaCO3 not organometallic. BCH3 taken twice. R2Si silicones, R2SiO and taken twice. Organometallics. NCH3 nitrogen connected with carbon, no. CaC2 calcium carbides. B boron connected to OCH3 groups, like oxygen is connected to boron now. It is also not organometallic. CaCO3 not organometallic. So list down the compounds which are organometallics. Of course, in our 12th standard, we only look about few compounds of these. Okay, not everyone, because that will be looking out to higher order chemistry. In the MSc and BSc, you will be studying more about organometallics. In here, in your 11th and 12th standard, you will look majorly about Grignard agent and dialkyl zinc. You have some compounds like silicones in the discussion of P block. Yes or no? But major discussion will be on Grignard agent. Fine, students. Okay. So these are the compounds or organometallic compounds where carbon is connected to metal or metalloid or non-metal like boron, phosphorus. In the next class, we'll be looking at applications of our coordination compounds and we'll solve few examples. Fine. Thank you all, everyone. Bye-bye.
Thank you, sir.
Thank you,
Thank
sir.
Thank you, sir.
Thank you, sir.